Hello, students. Hello, statistics students. I'm going to do a final exam review recording for you. I'm going over the study guide, and it's to help supplement the other recording. So Mr. Trotman has made a video recording going over the final exam review guide as well. And so this recording is to supplement his recording, and it's going over the similar problems from the final exam study guide. Okay, so I hope that it's going to help, and that's the intent is to help the student. And so good luck on finals. And I'm going to share my document camera with you. Let's see. And let me share the screen. Advanced settings. There we go. And this is going to work. All right. Okay. So you want to, get your handouts out. I have this handout, and then there's also a template, right? So let me just show you the kind of document. I think it's helpful to have, your past study guides out, your past study guides for your quizzes and your tests. So you have PDFs of your past test 1, test 2, test 3 study guides, your quiz reviews or quiz study guides. That's also helpful. So, it's just, kind of like what they look like, right? So you have your study guide from your test. So that's kind of what my PDF looks like. So you should have 3 tests. And remember, we also made some study guides, like for your quizzes. Like here's the one from quiz 2, right? Quiz 2 review. So your teacher had prepared study guides for that. And then also, your important formulas should have those out. And then also, as part of your formulas, don't forget your standard normal tables, right? And then this is, most recently we used this for quiz 3, right? So the PPMC table, right? That was used for quiz 3. And this is very important too. We use this when we took the probability test, right? So you have your deck of cards, rolling dice. We use this part for quiz 3. We use this for chapter 5, right? Binomial distributions. And then it was also helpful for quiz 3, right? So we're using some of the vocabulary, just the vocabulary inequalities. So we don't have that out. And then I went ahead and also printed the template for showing your works. Basically, clean paper, right? Separated with lines, right? So I recommend you do that because it already has lines built in. But, and then just remember to pace yourself, right? Okay. All right. So we can get started. And I'm going to cover this time. Let's see. All right, so let's get started with that. Let's see. So I also have a PDF of the detailed solutions that I'll be basically going over those, just adding voice to it. So this is kind of what my PDF looks like, the detailed solutions. And so I'm going to basically just, be going over that, but just with voice, because otherwise you could look at that PDF document and review that, and it wouldn't have any sound to that. But let me just rewrite it and go over that. Basically, is what I'm trying to do, and could possibly help you with that, the things. So let's start with this first page. So use the given frequency distribution to find the class boundaries and the midpoint for each class, and then they want you to find the class width. Okay, so it says age at inauguration. That's some ages here, and then we have some frequencies. Okay, and then also remember with frequencies, there's also like a tally, right? So tally, if there's a frequency of 2, that tally would look kind of like that. There's a frequency of 7, the tally would look something like this. 1, 2, 3, 4, right? We have 5, right? 6, 7, right? Those are tallies. So it wouldn't hurt to show that. And if I start with the class boundaries first, what you want to know about class boundaries is they should have one additional place value than the class limits. I can write that down here. So class boundaries they should have one additional place value than the class limits, and they should end in a 5. Okay, so if you look at this 42, okay, I'm going to show here the class boundaries. Which I'll call CD, for class boundaries. And so I want to take 42 and I want to subtract 0.5. And 42 take away 0.5, you can do that on your calculator, is 41.5. I can show you that here. 42 take away 0.5 is 41.5. Okay, so the reason why I'm taking away 0.5 is, remember, they have to end in a 5. So your choices could be 0.5 or 0.05 or 0.005. Usually those are one of the 3 choices that you're working with. And so for us, the 42, this is the 2 ends in a ones, like these are counting numbers, ends in a ones place. So 1 decimal point beyond the ones place would be the tenths place. So this is tenths, hundreds, thousands. So following the ones place would be tenths, right? So you have the ones place and then decimal point, and then you have the tenths, then you have the hundreds, then you have the thousands. THS is on this side, right? And so the 42 is a counting number, starts in ones. So one that class boundary should have one additional place value than the class limits. So these are class limits. See class? These are class limits. And these are counting numbers, right? And so that's why I went with my choices, 0.5, 0.05, 0.005. I went with 0.5. So I'm going to subtract a 0.5 to all of my lower class limits. And then I'm going to add 0.5 to all my upper class limits. So for 45, I'm going to add 0.5. So 45 plus 0.5 is 45.5. Okay. And that's basically what you would do for all of these, is you would, with the 46 here, you would subtract a 0.5. And on your calculators, 46 take away 0.5 is 45.5. And then to the 49, you want to add 0.5. So 49 plus 0.5 is 49.5. And you basically, I'm going to do dot, dot, dot. You basically want to do that all the way to down here at the bottom, your last class limit. So this is class 1, class 2, class 3, class 4, class 5, class 6, class 7, right? So this is like class 7, or this is class 1. So 1, 2, 3, 4, 5, 6, 7, this last class limit. So this would be, again, 66 minus 0.5. And then over here you have 69 plus 0.5. So 66 minus 0.5 on your calculators is 65.5. And 69 plus 0.5 is 69.5. Okay. And you can see, if you also look at your teacher's detailed solutions, you can see here how I've done that for all of these, each one. Okay. And it's a multiple choice test, so I wouldn't expect you, if they ask you to find, like there just one says find the class boundaries. So if it's a type of multiple choice, maybe they would, select this, for example, this class boundary for class 2, maybe, And so I wouldn't expect you to do because it is a time test. So I wouldn't expect you to do every single one. There's no need for that. If it's a multiple choice test, you just have to show 1 or 2 examples and show your work. And I can see, okay, they know to subtract and add 0.5, and that will give you the credit. So you don't have to do every single one. I just did it on a detailed sheet for practice, but you wouldn't have to do it for every single one. And also, if it hadn't been a counting number, like let's say this is 42 to 45. Let's say it was 42, maybe 0.2 to, I'm just making this up, 45.7, just making that up. But what if it wasn't a counting number? What if it was something to the tens place? Then beyond tenths is the hundredths place. So then you would take 42.2, and then you would subtract 0.05, because remember it has to end in a 5, right? So this time we're here, you're subtracting 0.5. Here you're subtracting 0.05. And then you would add, so let's see what that would equal. 42.2 take away 0.05 is 42.15. So see how your class boundaries have to end in a 5. So see it's ending in a 5. And then you would take 45.7 and then you would add 0.05. So 45.7 plus 0.05 is 45.75. So class boundaries have to end in a 5. Okay? And then if it had been, just making this up, but if it had been, let's say it was 42 point, I'm just making this up, let's say it was 5.7 to 45 point, and let's say it was 6.3. So I'm just making this up, but this was counting. This was 10th place, and let's say these are class limits. So let's say you had to the 100th place. So beyond 100th place would be thousands, right? So class boundary should have one additional place value than the class limits. So then beyond 2 would be 3 decimal places and ending in 5. So if you had something like this, then you would have to use the 0.005. So you would have 42.57 take away 0.005. So how much would that be? That would be 42.57 take away 0.005 is 42.565. And then you would have to do 45.63 plus 0.005. So this 45.63 plus 0.005. And that's 45.65. So that's just to practice in case, on the final, if you get something similar, but let's say they change the class limits and they're not counting numbers. Let's say they change the class limits in their 10th place, or they change the class limits in their 100th place. Then you want to be able to subtract according in this way, according to how the class limits are given. Okay. Okay, now going on to the midpoints. For the midpoints, your formulas are that you can take your lower class limit and your upper class limit and then divide that by 2. So the formula would be for the midpoints, which we call x sub m, right? The midpoint. You can take the lower class limit. See, this is class limit. So the lower class limit plus the upper class limit, and then divide that by 2. And on the calculator, you do need to put parentheses in the numerators. So you would take 42 plus 45 and put that in parentheses and divide by 2. And that would be, let's see, so parentheses 42 plus 45 in parentheses divided by 2 is 43.5. Okay. And you could do that, you know, that's how you will find all of these midpoints. So if I do dot, 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 if I go down to this last one, you're doing the lower class limits. So see, these are the lower class limits. These are the upper class limits. Lower class limits and upper class limits. So you would take 66 plus 69, take the average of that, and divide, add them up and divide by 2. So you need the parentheses. 66 plus 69 parentheses divided by 2 gives you 67.5. If you don't put parentheses, I'll show you how it will come out wrong if you don't put parentheses. If you do 66 plus 69, and then you divide it by 2, but you don't put the parentheses, see how you get something different? See that? So you do need to put the parentheses, and oftentimes that's a mistake. That's oftentimes why students miss something on the test, is because they didn't put the parentheses on that. Now, you can also find your midpoints by taking an average using your class boundaries. You can also see CB stands for class boundaries. You can also take your lower class boundary and then your upper class boundary, add those up in parentheses and divide by 2. So these are called lower class boundaries, and then these are called upper class boundaries. So these are lower and upper class limits. These right here are lower and upper class boundaries. So the formula would be or lower class boundary plus upper class boundary, take the average. So you add them up, divide by 2. So if I do that to show you right here, if I take, let me see, or you can take 1.5. Actually, let me do it for the bottom one. So let me do it for the bottom one. So let me erase this. Put down here. Or so let me take these. Lower class boundary 65.5 plus upper class boundary 69.5, and then divide that by 2. That should also give me 67.5. So let's check that. So we have parentheses 65.5 plus 69.5, close parentheses, divided by 2. Oh, I forgot to put divide. Let me do second enter to copy that, and then backspace, and then put divided by 2. Okay, there we go. See how we got 67.5. You just have to be careful. One little mistake, one little forgetting one little thing, you mark that wrong. So you have to be careful with that. Okay. All right. Okay. Let's see. Oh, now we need the class width. The class width. Okay, so you want to be careful with the class width because to find your class width, you're supposed to take your upper class limit. So you see these are upper class limits. You're supposed to take your upper class limit like from class 2. So that here's class 2 right here. So take your upper class limit from class 2, and then we're going to subtract something. Upper class limit from class 2. So here's class 2, and here's your upper class limit, which would be 49. And then you're going to subtract the upper class limit, but from class 1. So again, the upper class limit, but from class 1. So it's 45. Okay, so we're doing kind of like this. So you're doing 49 minus 45 is 4. And class width is CW. CW. That's your class width. So you're supposed to basically what you're doing is you're subtracting, but vertically, not horizontally. You want to subtract vertically from the, or you want to subtract vertically from the class limits. Okay, from the class limits. Okay, now if you can also do the lower class limit okay, lower class limit, like let's say, let's pick another class. Let's pick on this one. So class 1, class 2, class 3, class 4. Class 1, class 2, class 3, class 4. So you could do the lower class limit in class 4 minus the lower class limit from the previous one from class 3. Okay. So if I'm looking at class 4, I'm looking at the lower class limit, which would be 54. And then I'm going to subtract the lower class limit from class 3. So this is class 3, which is 50. And you see that 54 minus 50 is 4. That's your class width. It does give you 4. And I can do this, so I can do an arrow like that. So you do want to subtract vertically. You do want to subtract vertically, not horizontally, not horizontally. If you do horizontally, you won't get the right answer. If you do, just make a note here that 45 minus 42 is only 3, and 3 is wrong. If you subtract vertically 45 minus 42, that gives you 3. So they cannot both be correct. Like here we're getting 4, and here you're getting 3. 3 is the wrong class width. Now, if you insist on subtracting horizontally, what you can do is subtract horizontally, but not from the class limits. You can subtract horizontally from class boundaries, and that will give you the correct class width. So I can say, or use the class boundaries, and then you can subtract horizontally. So for example, if I use these class boundaries and I subtract horizontally, first the larger minus smaller, you would do 45.5, take away 41.5. So 45.5, take away 41.5. So 5 take away 5 is 0. Bring down your decimal. 5 take away 1 C is 4. And 4 take away 4 is 0. And that would be your class width. So you do want to subtract horizontally. You could, but you would have to do that from the class boundaries, not from the class limits. Okay. All right. Okay, so that's very important. And you want to show your work. So you have to show your work. So don't do it in your head. You can do it in your head to check, but you need to put some kind of arithmetic down on paper. And that would be the arithmetic that you want to see. Okay. The subtracting. Okay. Or like the subtracting and adding the 0.5. That's showing your work. Or midpoint is taking this average. So that's showing, this is showing your work. This is showing your work, right? So these are ways to show your work. So here you're showing, you know, the arithmetic, right? You're showing your arithmetic here, okay? That's showing your work, okay? And then if you're going to go with the boundaries, then that's showing your work for the what you're using, okay? These are all correct. Okay, so then let's see. Next problem, okay, there's 25 problems. So that was just the first. Now, for number 2, ages of the vice presidents at the time of their death, or the ages of the vice presidents of the United States at the time of their death are listed below. So let's see. So these probably don't have all the presidents that we had, but not all of them have passed. But it's interesting. So some have lived to age 90, which is really nice, right? 90. And I think the youngest, that's a pretty young age, right? 54. Oh, 51. Look at that. 51. That's really young. He passed on at that time. Okay. And 80s, that's a good age. Okay. All right, so these are the ages, and these are of the vice presidents, not the presidents of vice presidents. The time of death are listed. Use the data to find the upper and lower limits of a frequency distribution with 8 classes. Find the upper and lower limits. Okay, so they want you to, like over here in this problem, the class limits, they want you to find the upper and lower limits of a frequency distribution. So they basically want you to create this. They want you to create this is for this data, okay? And this data is probably out of date too, because I think, recently didn't President Carter recently pass on. So I don't think they have his data in there. So this is, I'm not sure how up to date this is. So let's see. So you would begin by finding the class width. But when data is given like this, you cannot find the class width the way we did over here. The way we found the class width here was because we already had class boundaries and we had class limits. Here we're kind of building this from scratch. So instead, you do need a different formula. You would have to take the range, and the range is the largest data minus the smallest data, and then you'd have to divide by the number of classes chosen, basically by the author. So they will tell you how many classes they want. And they said that it was 8. See, they tell you it was 8 classes. So this is going to be divided by 8. And the largest data value is going to be 98, I believe. And then the smallest data value is, we talked about that, it's 51. Okay. All right. So we type that in. 98 minus 51 is 47, and then we divide it by 8 is 5.875. So I can either type it in one big swoop with the parentheses, or I can type it in a couple pieces, but we still get 5.875. And you will have to round up. This the requirement is to always round up. So 5.875 is a number that's between the counting numbers of 5 and 6. So when they say round up, you're rounding up to the next, you're going to round up to the next counting number. So 5.75 rounds up to the next counting number, which would be 6. Even if it had been even if it had been like 5.126, I'm just making this up, even 5.126, even that rounds up to 6. Okay, so rounding up is different from rounding off. Okay, rounding up is different from someone telling you to rounding off, like rounding off to the tens, rounding off to the hundreds, rounding off to 1,000, rounding off to the ones place value. That rounding off is different from rounding up. So a number is rounded up if there's a decimal remainder when dividing. So a number is rounded up to the next counting number. Okay. And let's see. So now that we know that we have the 6, what was the 6? It was the class width. So the class width is going to equal 6 because we rounded it up to 6. So that's going to be 6. Okay. So you do that when you have a lot of data given. So it's different from this kind of class width where you already had the class limits, right? So it's different. So now they want you to create something like this. They want you to create class limits. And because you have this data is counting numbers, these are counting numbers, then your class limits will also look like that. You will have counting numbers in your class limits. So I'm gonna get another sheet of paper, and you always start the first with your class limits. You always begin the first class. It always begins with the smallest, begins with the smallest data value, which remember, I believe it was 51. Remember that? It was 51. So the first class begins with 51. And then to get the second class, you want to add the class width. So you want to add the class width to the smallest data value. And what that gets you is to get the lower class limit of the second class. So you want to take 51, and remember the class width that we said was 6. So 51 plus 6 is 57. And you basically want to keep adding 6. You basically want to keep adding the class width equaling 6 until you have 7 classes. Or let's see, 8, right? 8 until you have 8 classes. Because remember, the author told you that they wanted 8 classes. Remember, they said 8 classes. So you're going to take 57 plus 6. That gives you 63. That's going to be your third class. And then you're going to, 57 plus 6 is 63. And then you're going to add another, oops, you're going to add another 7. No, add another 6, sorry. Which is 69. And that's your fourth class. And then take 69 and that's 6. So that's 63 plus 6, which was 69, plus 6, which is 75. Sixth class. So 75 plus 6, that's the class width, is 81. And then seventh class, 81 plus 6, which is 87. And then one more time to get the 8th class, 87 plus 6, 87 plus 6 is 93. All right, and now we're not done yet because these are the lower class limits. Now you need the upper class limits. So now you need these up here now. These. Okay. So what I would do is there's a relationship here between the upper class limit, this upper class limit, and this lower class limit here between the first and second class. This value we need to subtract. We need to subtract a value that ends in 1. And has the same amount of place values as the class limit values. So since your class limit, these are counting numbers, right? One's place value. Then when you say you want to subtract a value that ends in 1. So your choices are, do you subtract 1, or do you subtract 0.1, or do you subtract 0.01, or do you subtract 0.001? Like which one do you use? So you want to use one value that ends in 1 but has the same place values. So these are like counting numbers, so you would want to go with this one, counting number 1. And that's because right here you have 57. This is going to be calculated as 57 minus 1. Okay, so 57 minus 1 is 56. That would go right there. 56. Okay. And then the way to get the rest of this side is you just continue adding 6. So 56 plus 6 is 62 because you added 6. And then 62 plus 6 is 68. So you added 6 to that. 68 plus 6 is 74. If you added 6 to that. And then 74 plus 6 is 80. And then 80 plus 6 is 86. And then 86 plus 6 is 92. And then 92 plus 6 is 98. And so these now are your class limits. And if we were to do a check on the class width, check on the class width, we're going to subtract vertically in the lower class limits. So we do that. Let's say I pick these right here. Just randomly pick these here. So subtract vertically in the lower class limits using class 6 and 5. That would be 81 minus 75. 81 minus 75 is 6, which is the class width. And remember, that's what we had said. That's how we had determined it. Remember, we did say it's going to be 6. Okay, so I also wanted to do another check using the upper class limits. And let's say I just pick on this here using class 7 and class 8. So that would be 98 minus 92, and 8 minus 2 is 6. And that's correct, possible. Now, again, if I had class boundaries, then I could subtract horizontally if I had class boundaries, right? So if I had the class boundary, if I had 51 minus 0.5, is 50.5, and then 56 plus 0.5 is 56.5. And then if I were to find the class width by subtracting horizontally the class boundaries, not the class limits, but the class boundaries, then I'm looking at 56.5 minus 50.5. And 5 take away 5 is 0. Decimal point going down. 6 take away 0 is 6. 5 take away 5 is nothing. So 6.0 is the class width. Do you see how we get 6? So that would be okay to do that. Okay. And that's what they were asking for number 2. Use the data to find the upper and lower limits of a frequency distribution with 8 classes. Okay. So they wanted you to create that, right? That was all they were asking for. They didn't ask for the midpoints or the class boundaries. So, all right. Okay. So now let's go to next page. Display the data in a stem and leaf plot. Okay, so I can increase this. Here's your data here. You see that? So we start with, if we start listing our data from smallest to largest, this this looks like 74. So it looks like this is 74 followed by 76. This looks like 72 76s. And then we have right here 79. Let's see. Notice that. So we had 74, 86, 76, 79. Okay. Then if you look at the going to the 80s, we have 4 80s. So start another one. 80, 80, 80, 4 80s. You see that? 1, 2, 3, 4. Then we have an 82. We have an 84, another 84. We have 485. And then 289s. I'm trying to keep this on the same window. Let me squeeze it. Let me squeeze an 84 in between here. And then we had 289s. See that right here? Right here, 89s. Okay, then we have 290s and a 93, a 94, a 95, a 96, and then a 90, a 98. Okay. So since our data values consist of 2-digit numbers, okay, so all these consist of 2-digit numbers, then our stem should be made up of leading digits. When you make your stems, you have your stem and leaf plot. Stem is made of leading digits that have so stem is made of leading digits that has this formula of 2 digits minus 1. So 2 digits, because these are 2 digits minus 1 is just equal to 1 digit. So that means 1 digit in our stem. So we have a stem, and then we have a leaf. And we've got 1 digit in our stem. So what I'm going to do is go back and underscore the first digit in our data. So in our data, the first digit, so that's our first stem, is 7. And then see, these are all first digits, right? all these are eights, right? All these are eights. So I have eight. And then 9, first digits. Okay, so now for our leaves are going to be these remaining digits that are not underscores. You see 4, 6, 6, 9. That's your leaf. So that's 74, 76, another 76, and then 79. Okay, so you have the stem part and then the leaf part, and that represents your data. So 74, 76, 74, 76, 76, 79, 76, 79. Okay, and then I have for the eights, they end at 80s, right? So 80, 80, 80, 80. So that's 4 zeros. So I'm going to try and like line them up like this. And then you have an 82, and then you have an 84, then another 84. Then you have 1, 2, 3, 4, 85. So I'm going to put 5, 5, 5, 5, 5, 5, 5, 5, and then 89, 89. So 89, 89. And then under the 90s, you have a 90, a 90, a 93, a 94, a 95, a 96, a 98. Okay. So what happens with the leaf, the trailing, the trailing digits become the leaves. The trailing digits become the leaves. And for the stem, the leading digits become the stem. So for the stem, the leading underscore digits they become the stem. All right. So in your data, if you had data that had more digits, like 3-digit numbers, like let's say you had data that had I guess like but maybe 329, 445 with 3 data values, let's say 698. These have 3 digits. So then in your formula, you would do 3 digits minus 1. And 3 digits minus 1 equals 2. So there will be 2 digits in our stem. So then when you have your stem, then you leave, then you would underscore the first 2 digits. So let's say here, this is 447, 140. Let's see, let me do it. Because let's see what that would look like. So that would be 32, and then 9, and then 44, but then you have 445, 447, 449, so 445, 447, 449, and then it's 69, 608. And let's see, that would kind of be the idea. And I think usually in your Alex programs, they usually help you build the stem. They usually help you build the stem. But I just made up these data off the top of my head, but the data would be closer. I don't think you would have so much of a gap in between, because you really shouldn't have a gap. See, this is 7, 8, 9. So you should have like 32 here, and then 33, 34, 35, 36, right? So you shouldn't have so much of a gap. Let me see if I have, I don't know if I printed, I have a section about it in my notes, in our class notes. I have a section about, but I don't think I printed that. It would be, let's see, it would probably be in chapter 2. Yes. I don't think I did print some pages. And this test is going to be multiple choice, so you'll kind of be able to, pick a best choice. But let me just see, I have some papers here. I'm just have that example, because I know I have a page in my notes, but I'm not sure if I should print that. Remember it was when we were doing like this salad dressing problems. I don't know if you remember that or not. I'm gonna try to print some things, but maybe if you have maybe that particular sheet. Let me see if I can see something up on the text. Let me just look in the text and see. But that would be in chapter 2. with other types of graphs. The data I see in here are like 2-digit numbers. I don't think I see any with 3-digit numbers. They just have 2-digit numbers. Yeah, all the examples I'm seeing here. I don't see anything with 3-digit numbers. So probably you'll just keep to 2-digit numbers. Let me look at the exercises. And I do see problem 18, construct a stem on leaf 5. 18. I think we did do that one in our notes. And it does start off with 100. Let me see what the smallest one. Let me show you this one I'm looking at. See that problem there? That's in section 2.3. And I think this is page 92 in my book, but it's going to be in section 2.3. So on the ebook, it might be a different page, but it would still be the same section. So that's 2.3. But you see how you have 3 data. Most of the data has 2 digits, but this one does have 3 digits. And so, are they in order? They don't look like they're in order. You definitely want to sort them. You can sort them on the calculator too. And you could put the data in and then sort them from smallest to largest. It does look like it starts with 100 being the smallest part. And then you'd have, yeah, because you want to do like 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, right? And then when you get to 110, you would have another stem. So again, it's 3, take away 1. That's the formula. 3 digits in your data, take away 1 is 2. So your stem would have 2, but this one would start like with 100. And so let me just jot down a few of your data values there. So like we do like, we do over here data. So I think I see 100. Let me see how many hundreds I see. 1, 2, 3, 4, 5. I think I see 5. 1, 2, 3, 4, 5. I think I see 500s. And then I don't see any 101s. Let me see. Right? I don't see any 100. I do see 500s, and I don't see any 101s, 102s, 103s, 104s, 105s. I think the next thing I would see would be 110s, right? So 110, how many do you see? I think I just see 2 110s.
Any 111, 12, 13, 14, 15. So no, 15. Most of them end in the 0. You do see some 145s. There's a few 5s, but everything ends in 0. So I think that's going to help us then. Because after 110, we would jump to 120. How many 120s do you see? 1, 2, 3, 5, 6. I think we see 6. Do you think you see 6 of them? 620s, I think. And then how many 130s do you see? We'll go up to 145s. We won't do the whole problem, but how many 140s do you see? Well, excuse me, 130s. I think I see 5 of them also. So I think I see 5 130s. And then we'll go to the 140. So what I'm doing is kind of putting the data in order. How many 140s? So there's 2 145. There's a 140 there. Another 140. Looks like you have 4 140s. So there's 1, 2, 3, 4. Looks like you have 4 140s. And then 45. 3, right? 1, 2, 3. Looks like you have 3 145s. I think there's 3 145s. Okay, so the idea is you would do 3 digits. This formula, 3 digits minus 1 is 2 digits in your stem. So here you have your stem, then your leaves, and then you could start with 2 digits, right? 2 digits, start off with 2 digits. So you have 10, and then you'd have 1, 2, 3, 4, 5 zeros. And then you'd have after 10, you have 11. So you have 2 zeros. So there's 110, 110. Then you have 12. You have 1, 2, 3, 4, 5, 6 zeros. So try and keep them kind of aligned. And then you have 13. 1, 2, 3, 4, 5 zeros. And then 14. 1, 2, 3, 4 zeros. And then 3 5s. And that's kind of the idea of your stem if you had more than 2 data values. Okay. So generally you don't want to skip anything in between. So you see this is really nice. 7, 8, 9. You have a single stem. 10, 11, 12, 13, 14. So this really is not acceptable. But remember, I just made this data up off the top of my head, remember? So, but usually when that is given, they won't be that spread out because you really shouldn't have big gaps like that, like jumping from 32 to 44. It should be consistently consistent. So this is not a very good example, but I was just trying to get you the idea of the stem and the leaf. That would be 329, 445, 447, 449. Okay. And these are not back to back stem and leaf pods. These are just um, one-sided, right? Because we did do some that were back to back. So when you do these one-sided, they go from small to large. So your leaf, that's why I was putting these in order. These are small to large. So these are leaves go from on this side, small to large. If you had a back-to-back stem and leaf plot and you had two data sets, and then you had another data set on this side, you have to do more data on this side. Then on this side, it would be from large to small, large to small. So you would have to put these data values from large to small instead on this side. So we didn't have anything. We don't have any back-to-back two data sets on that. Okay. All right. I hope that helps. You can, if you want to review your notes, you can go back to your Canvas course, and this was section. What did I say? It was 3.3, right? No, 2. Right, it was 2.3, wasn't it? And I think I said it was page 93. So it's section 2.3, and I think this was on page 93 of your textbook, or page 92 of your textbook. If you want to kind of look at your ebook, see that, or go back to your PDFs and your module in Canvas and go to section 2.3. So I know I had a few other examples of that there. Okay. All right, let's see. Number 4, a stem and leaf plot is given below for Latin test scores taken by sophomores at a university in South Texas in 2015. So here's a stem and leaf plot. So you see how it's in order. So this is in order. So this must be the stem. And these must be the leaves. You can see it starts with 0. 0, so the smallest data was 4. And this is 18, so I guess I could do this. That's 8, so this is your data is 4, and then 18, 19, 23, 24, 26, and then all the way down here, these are like a dot, dot, dot. This is 60, 62, 63, 65, 67. If I were to do that, okay? So a stem and leaf plot is given below for Latin test scores taken by sophomores at a university in South Texas. State whether the distribution is it about symmetric, or is it right skewed, or is it less skewed? Okay. And so I'm gonna look at the book. This is section 2.2. Also, section 2.2. This is on my book. It's page 63. This says when one is describing data, it's important to be able to recognize the shapes of the distribution values. This is a bell-shaped distribution has a single peak, which is in the highest column, and tapers off at either end. It is approximately symmetric. It is roughly the same on both sides, like the same amount of data in your columns on both sides of the line running through the center. So if you take a look at that, it says figure 2.7. So you see here's your peak, and these would have the same amount of data, more or less, on both sides of the opposite sides of the peak. That's kind of bell shaped. Okay. And then this is your right skewed. See, this is your peak, the highest column. And then look at the data. If you count like the data values in your columns here. So let's see how your book describes it. The right skewed, and then there's also left skewed. See, left skewed is your peak, highest column. And then look at all these data values on this side. So let's see what your book says about that. It says that when the peak of a distribution is to the left, so when the peak is to the left, and the data values taper off to the right, a distribution is said to be positively or right skewed. See figure 2.7. Okay, so the peak is to the left, and then the data tapers off to the right. So we'll see that. Okay, so the peak, this is the peak right here. The tallest column is kind of to the left, and then the data tapers off to the right. Okay. Whereas left skew, it says when, so here's your left skew. When the data values are clustered to the right and taper off to the left, so you come taper off to the left, a distribution is said to be negatively or left skewed. Okay. So here we could say that the peak of the distribution is to the right. So we could say like the peak of the distribution is to the right, and the data values are clustered to the right, it says, and they taper off to the left. Distribution is said to be negatively or left skewed. Okay. So I like how if I kind of write it opposite to what this said when the peak of a distribution is to the left. I'll say when the peak of the distribution is to the right, and the data tapers off to the left, the distribution is said to be negatively or left skewed. Okay. Kind of reword that a little bit. But what you do is you can turn this data to the side of this. And then you outline the curve of the distribution. And you can turn the shape side up, and you outline the curve of the distribution. And you can see then that it kind of resembles on your graph. You can see that kind of resembles this one right here. See that? See that? And we could put it side by side. Can you see that side by side? This here. Kind of looks like that. That's fit. Okay. So what I can say is I kind of use what the book was using. When I kind of switch it off from what it was saying on right scoop. So I'll say when the peak of the distribution is to the right, and the data values taper off to the left. The distribution is got to be negatively or less skewed. Oh, I'm sorry that you can see that. Hmm. So you can review that in your book. That's in section 2.2. And for me, in the book it's page 63. So you have access to your ebook and your Alex platform. All right, so you can see here, this is the peak. If you look at the peak, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You have 14 data values. And this side is just only has 1, 2, 3, 4, 5, only has 5 data values. But then look at all these over here. 1, 2, 3, 4, 5, 6, 7, 8, 9. This has 9 data values. This one, 1, 2, 3, 4, 5, 6, 7 data values. This one has 1, 2, 3. This one has 1, 2. So I'm not counting this. I'm not counting the stems, right? 1, 2, 3, 4, 5. Yeah, I'm not counting the stems. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I'm not counting the stems. And then this one has 1. And these are data values. So yeah, you can see this is your peak. It's the highest column here. And you can see that most of the data values are on the, okay, so this is your peak. And you can see that most of the data values taper off to at the left of the peak. Left of the peak, right? Okay. All right. Okay. So I hope you have enough time to write that. If not, you can pause it and I'm gonna continue with 5. Okay. Let's see. I was just looking at what had written. I was looking at my detailed solutions, and I don't really like so much. Let me just show. I don't really like what I have written here so much. I like what I have written right now, but I was just looking back at this, and I don't really agree with what I have here. I put the tail is located on the left-hand side. So I guess I'm looking at this like this little part here, okay? But it says with few smaller values showing up on the left side. That's not really true. But most of the data are on the right side. It's not true. So the distribution is roughly left skewed. Yeah, I don't like that write up, right? I don't like that write up. It doesn't sound correct on this one. So it needs to be edited or fixed. I like what I have here. This is more reflective. So you look at your peak. Here's your peak. When the peak of a distribution is to the right side, so that's kind of what's happening here. You have your peak, and it's more on the right, and then the data is tapering off on the left-hand side here. You can see the majority of the data is to the left side here. So this is left skewed. So I do have here that it is left skewed, but I don't like the justification. This justification is off on that, okay? So I should probably to fix that, but if you're watching this video, you got it right here on the video from here. So apologize for that. It's kind of awkward page there. Okay, let's look at 5. You are see. You are taking a class in which your grade is determined from 5 sources: 50% from your test mean, 15% from your midterm, 20 from your final exam, 10 from your computer lab work, 5% from your homework. Your scores are 86 for the test mean, 96 for the midterm, 82 for the final, 98 for the computer lab, and 100 for the homework. What is the weighted mean of the score? Okay, well, the formula, let's get the formula. The formula for the weighted mean is, this is X bar, right? That's where X bar means mean, but for weighted, you do the summation of a product of W times X divided by the summation of W. And I think I have, if I reference, excuse me, if I reference the first test we took, or look for the first test we took, I think we had if I look for the first test we took, I think we had a problem like that. Let's see. Do you remember this? Let's see. That's similar. Look at that. That was this is the test review, right? This is the test practice test from the first test. Okay. So we had the grades as X, and then a weight, we had those as the percentages. And here's this formula, see, for weighted mean. So we do something similar. Let's see. Yeah, I think that would be very similar, wouldn't it? So we would do, I don't know if I could do a little table. Let's see. So some of the grades, it was, you have your paper was 86 was the test mean. And that was 50%. So you have to move your decimal 2 places to the right. So that would basically be 0.5. And then the midterm was 96. That was 15%. It's 0.15. And then you had a final. That was 20%. Kind of like our final, and the stats test is 20%. You can do 0.2 or 0.20. And then you had a computer lab. It was a 98, and that was 10% of the grade. And it's not going to fit here, but you also had homework. I'm going to put it up here. And the homework looks like it was 100 average, 100, and it was 5%. And that's you will not make a mistake, there's 0.05. Okay. So then you're doing, when you're multiplying W times X, you're doing, and they say W times X, but you could also do X times W if you want to, because we have it set up here. You can also do X times W, that would be okay, because multiplication is cumulative. But you're doing 86 times 0.5 plus 96 times 0.15 plus 82 times 0.20 or 0.2 or 0.20 plus 98 times 0.1 plus 100 times 0.05. I just put a bracket around that. And then all that divided by the summation of W, which is all these percentages. So if I add all of those, summation of W is 0.5 plus 0.15 plus 0.2 plus 0.1 plus 0.05. Okay. So let's see, when we put all that in the calculator, so I do 86 times 0.5, that's 43. Plus 96 times 0.15, 14.4. 82 times 0.2, 16.4. 98 times 0.1, 9.8. 100 times 0.05 is 5. Okay, so what is all that? 43 plus 14.4 plus 16.4 plus 9.8 plus 5 is 88.6. And on the bottom, at the bottom, the 0.5 plus the 0.15 plus the 0.2 plus the 0.1 plus the 0.05, that just gives me over 1. Because that would have been 100%. And when you move your decimal 2 places over to the left, that gives you 1. And that's what happened here on this practice test. You added all these percents up, 60, 70, 90, 100%, and you move your decimal 2 places to the left. That gave you 1. See? And then here we multiplied 0.1 times 93, 0.3 times 96, 0.6 times 100. So then we added those up, and this one was a 98.1. That's similar to that we got. So this would be 88.6 divided by 1 is equal to 88.6. Okay. Now, sometimes, let me look at something. Sometimes what happens, so I have to let you know too that sometimes on your weight is not always in percents. And sometimes, sometimes they pulled some of these problems out also on a final. Sometimes your weights, so I'm gonna put grades. Okay, so in this problem, your weight was a percentage, but that's not always the case. Sometimes your weight could be in points. And, you know, some teachers, I mean, I usually do percents, but there are some teachers in different disciplines, maybe like psychology, sociology, or maybe music or government. Sometimes teachers use points, not percentages. They use points. So you need to be familiar with that. And that's if you get a problem like that that gets circulated on the final. Sometimes they have like a variety to pull from. Sometimes there are some problems that on the weights they're not by percentages, they're by points, and that can throw you off because what that means is that the grades might be more in a percentage. And so, like, let me give you an example. Let's say we say you have tests, and I'm just making this up. Let's say it's 85%, but on your weights, let's say you have points, and let's say it's um I'm just making this up. Let's say it's 73 points worth. Okay, so you still have this formula. It's still a weighted mean, x times w over summation of w, but you've got this point system here. And so let's say you have a midterm test, and let's say that was 70%. And let's say the weight on that one is more. Let's say it's more. Let's say it was just making this up. Let's say it was 85 points. And then so you have it. Homework. So they're 100%. And let's say that's worth less. Let's say it's worth 20 points. And then let's say you had this. What else could you have? Let's see. I was making this up. So I guess let's do one more. The final. Let's see. Student A. I didn't understand. Let's say this was more points than 2. So let's say this was more. Let's say this was 8 points. Just making this up. Okay, that's good. That's an example. I just want to show you an example when your W is not always a percentage. Sometimes some teachers make points out of that weight. And so then your total would be, when you add all those up, let's see, 73 plus 85 plus 20 plus 98. Looks like 276. So here I have a summation of W from adding up all my weights. It's 276. So then the top part is X times W, right? So it's going to be, it's 85, and these are percentages. So this would be 0.85 if I give it to you in percent times 73 plus 0.7% times 85 plus, this is 100, so you give it over 2, so it's 1 times 20 plus 0.91 times 98. I put a big bracket all over the summation of W, which is in points, 276. Okay, so let's see. So you have 0.85 times 73 0.7 times 85 1 times 20 is 20. 0.91 times 98. Excuse me. Now I'm going to add those up. So 62.05 plus 59.5 plus 20 plus 89.18 plus 230.73 divided by 276. And oh, I know what I will have to do. So that gives you 0.8359782609. But what I need to do to this formula, okay, what I need to do this formula, um, when I've done it like this, is this formula, then I have to change it to times 100%. Because I made these into percentages here, or into decimal. I changed this percent into decimals. So then I'm having to, that's why it's awkward here. I have to do it times 100%. See. Times 100%. Times. So if I do times 100, yeah, let me just say times 100. Let me just say times 100 is 83.5978269. So if you're rounding up to the nearest whole number, this is the ones place. But is this neighbor 5 or more? Yeah, it's a 5. You add 1, so it'd be about 84. That'd be about an 84. Give or take on that. And usually, what do we say about the rounding rule? Let me go back to it. We said about rounding over here. We say over here, raw data, said raw data, the X was presented as counting numbers. So because this was counting numbers, this had to be one decimal place beyond the counting numbers. Over here on X, 85. I guess I should do, because it's 85, 70, 100%. If I round it to one, I probably should have this round to one decimal place. So I probably should do, instead of counting numbers, I probably should do the 10th place. Okay. So this is 83. 83.59. So I should probably round this to the 10th place then. And look at the neighbors. The neighbor 5 or more, yeah, it's a 9. So add 1 to that. Could be 83.6. Which I rounded one decimal place beyond all the data, the X values were. So since it was 85, 70, 100, there were no other percent. One decimal place beyond that would be 10th place. Okay. And I think that if I had not changed them to percents, if I had left it at 85, if I had just done, if I had just done 85 times 73 plus the 70 times 85 plus the 100 times 20 plus the 91 times the 98, that would have given me this 23073, and then divide that by 276. Yeah, so that would have been, if I had just done like the 85 times 73 plus dot, 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 and then, all the way to the 91 times 98 divided by the 276, then I don't have to, multiply the formula by 100. Then the formula can stay summation of x times w over summation of w, which is then 83.5978269. And then when I round that, there's tens, and I'll have to add 1 to the neighbor. Well, I have to add 1 because the neighbor is at least 5. The neighbor is 9. So I have to add 1 because the neighbor is at least 5. It's a 9, so it's more than 5. Add 1 to that 5, and it gives me 83.6. So yeah, so to keep this formula without multiplying by 100, then I would have just worked with the 85 times 73 and 70 times 85. Okay. But if I want to work with the percent, 0.85 times 73, that would be okay. But then you see how small this is here. So then I have to multiply it by 100 in the formula. But the idea is that the main thing is to stress is that, the problems in your weights, sometimes the weights are in percentages, but sometimes the weights are in points. So the weights are in points. There's no need, to move your decimal or anything because it's different. Over here, our weights were in percentages in this example. In this example that I made up, sometimes your weights will be in points. So I just wanted to show you it's similar, but it's different because it's a point system. Okay. All right, so just be familiar with that. So if you see that in the final, you won't be surprised by it. I don't know if in Mr. Trotman's video, I haven't looked at his recording, but I don't know if he talked about how sometimes your weights can be points. I don't know if I'm not sure if he covered that or not or mentioned that. That would be helpful if he did. Okay, let's see. All right, so that was like another part of, this is another example of 5. So this is another example, but using points. Another example using points in our weights. If that can happen. That's 5. All right. So now let's look at 6. Compute the value of the correlation coefficient. So that's R. Round to the thousands place. That's 3 decimal places. Does the result suggest a strong positive linear correlation, a strong negative linear correlation, or a perfect positive or negative linear correlation, or no correlation, or a weak linear correlation? Okay, let me see. Let me see if I have anything that talks about the weak and strong. I'm pretty sure I printed something kind of like my notes. I think I did print something supplementary to talk about that. It's on that handout. One point when we were supposed to do covered correlation. 10.1, 10.1 handout. Remember this handout, this 10.1 correlation handout? That was when we needed that. We could have used that when we were taking quiz 2. So, see, correlation coefficient. Okay, so see this here? See, it says strong negative linear relationship, no linear relationship, strong positive linear relationship. So when the correlation coefficient is close to 1, positive 1, strong positive, strong negative, and they're both linear relationships, but when it's close to negative 1, and then there's no linear relationship when it hovers about 0, when it's close to 0. And that's basically what this paragraph is saying. Okay. Now, on your calculators, you have to make sure that this is turned on. So see this part here? You have to press the second catalog, and that's on 0. Press second 0. Use the arrow keys to scroll down to diagnostic on. Hold the down arrow to scroll faster. Press enter to copy the command to the home screen. Press enter to execute the command and see done. So you do have to do that. Like, make sure you can turn that off. So turn your calculator on. Press the second button. Here's the second button. Press the catalog button, which is on 0. So see here on 0. See it says catalog. So press that blue and go all the way down. You can hold it down and go all the way down to diagnostic on. It's alphabetical. So C's and then D's. And you want to make sure that you turn it on, diagnostic on, and hit enter. And then hit enter again. And then it says done. So you do want to make sure that's turned on, that's refreshed, okay? So for this activity. So that's from this is chapter 10, section 1. So that was when we took quiz 2. Okay, needed that. So then when we do this, we're going to use the linear regression t-test features to find the correlation coefficient. You're going to press stat, you're going to tab to the test menu, and you want to go to linear regression test, which is F. But if you don't want to scroll all the way down to F, this is faster to press the green button, alpha cosine. Alpha cosine will take you to F. So, and we also have to put the data in. We do have to put the data in also. Enter L1 for the X list, enter L2 for the Y list. So we need to put in our X and Y data. So, here's our X data and then our Y data. So you need to put that data in. So you want to use stat, right? Stat, and then that one edit. And then enter. And then you want to clear your data. So I'm going to go back, tab back here to L1 and go up to the top. And press clear and enter. And that's to clear the data in your column. Don't hit delete, because if you hit delete, then you're gonna lose your your L1 columns and disappear, and you won't have an L1 column anymore. Which is, I mean, okay, you can work with L2, L3, L4. You have a lot of other columns you can work with, see. But you don't want to hit delete, you just want to hit clear. So just go to the top, hit clear, and enter. And then do that for L2, go to the top, hit clear and enter. And then start inputting your data. So I'm inputting this data into my first column. And then I'm gonna go to my second column. So this is like for L1, and then this is like for L2. So I've got CO2 emissions in millions of metric tons, and then GDP trillions. That's money. Okay, so now I'm gonna go to L2. So tab to L2 and then input that data. And hit enter. So after you type the value, hit enter. I don't need that 0 there. I can just type 264 and I'll be fine. And just make sure that you double check your data before you hit enter. You should double check right here and make sure it's right. And once your data is in, then we should be able to go back and do what we were saying here. And after we enter data, so we can do stats, tab to test. And I think I also have that on the page. Let me see what I have here. I think I summarized that handout. I think I summarized that here. Find the correlation coefficient, which is R, not R squared, but R. It's called the Pearson product moment correlation. So that's a PPMC. We had like a PPMC table, remember, on quiz 3. It's kind of related. So find the correlation coefficient R using the linear regression test on the theoretical calculator. So input X list into L1 and input Y list of data into L2. Press the stat key, tab to test. So press the Stat key, tab to test, and go to F linear regression test and hit enter. So you can go all the way down. You're going to pass numbers like 1 through 9 or 1 through 0, and then you're going to go alphabetical A all the way through F. That's the, just scroll down to that. The faster way, I think, is to do, even though it doesn't say it on this paragraph, it's alpha cosine. I think if you do alpha and then cosine, to see there's an F on it. See that little green F? Alpha cosine will take you to that as well, faster. Otherwise, you scroll down all the way past the numbers, like 1 through 9, and then 0, and then A, all the way to F, and then hit enter, and then it'll take you to this page. And then you just want to tell your calculator where did you put your X data and where did you put your Y data. So you hit second and the number 1 to tell the calculator, hit the second button and then number 1. And then here you hit the second button, number 2. That's how you name your data. So that's already L1. And then this is second and 2. Yeah, that's the L2. Okay. So your paper here says frequency should be 1. And on your test, your hypothesis testing, you want this p-value not equal to 0. So you want the first one. Okay, so you want this frequency to be 1, and then you want this first test. You don't want it on here or here. So you can use it's, like you don't want that highlighted. If that's highlighted, you want to change it to this first part. So in your hypothesis testing, we need to set it up like your H1 setup, so it's equal to 0 or not equal to 0. This is a left tail test. This is a right tail test. You want more like a two tail test. This is left, right, more like a two tail test. And I think I have it here. Let's see. So there's the one here on the frequency, and even though it doesn't have this highlighted, but it's not left or right, it's this first part we need to know. And then we do need this Y1 there if it's not already there. Oh, and the symbol was rho. The symbol was rho. I think I might have called it P. But I have here this. I don't know if you ever printed this handout out. I think this was in chapter 3. When you first start chapter 3, this is the Greek letter of the alphabet. And see this, I had called this P a while ago because this is capital P. But see this figure? That's called rho. They don't call it P, they call it rho. See, rho. So that's what that's called. That's reminding me of that here because I have that here. We need rho not equal to 0 highlighted, not the less than 0, not the greater than 0 on the 284. And so we say activate 1. Oh, press the vars button. So the vars button is located in between the program and clear. So we already entered L2 for regression equation, then press the vars button. And then you want to activate this one function, press enter. Tab down. So let's try that. I think I have it here. Frequency should be 1, and this is, we said this is rho. We want this one, this is rho. The first choice, not the left or right tail. Well, frequency is hit vars, which is right here. See that? So make sure you go down here, and you might not have anything there, but because we've already taken quiz 2, you should have a Y1 there, because you took quiz 2, you did that problem. But if not, hit the bars key. And then you hit Y bars, and then you want that one function. So hit enter. And then you want that Y1, so you hit enter. And see, so now if you didn't have it, now you should have it. And then we already put our data in, so now we should put it down and calculate. And it says after tab to calculate, tab down 4 times to look for R. The correlation coefficient determines the strength and the direction of a linear relationship between two quantitative variables. Strong positive relationships are close to 1. Strong negative relationships are close to negative. So let's go down, so 4 times, right? Tab down 4 times. So there's, oh, okay, there's R squared. You don't want R squared, you want R. Okay, there it is. See that? There's your correlation coefficient. And I think it sets you around to the thousands place. Tens, hundreds, thousands. So it's tens, hundreds. Tens and at the neighbors. Neighbor 5 and 1 no. So then you don't have to add anything to that too. Okay. And I'm just gonna go back. Remember, you said scroll all the way down to F, so or you can use what is the alpha, the green button, and then the cosine and Y, the cosine, because the cosine will have the F on there, and F is what has that particular unit. The regression t-test that we needed. I have a note here that there is like a generic answer key. The generic answer key for two different commands required. Let me see what I have. This is like a little. This is also another in your study page. The study page for the file. You have PDFs. So there's like just like an answer, not a detailed answer, but there's this solutions guide. But for problem 6, your teacher has, let's see, I have that on our handout. Let's take a look at that. Go ahead and read that. Okay, so this looks like I was summarizing this handout, in case you didn't have that handout. It looks like I was summarizing this here. That looks like what that is here. Look at this, take a look at this. This is saying, this is another way to get to it. And this you might be familiar because I think we used this for quiz 3, didn't we? When we were talking about multiple regression. I think we use this when we're trying to find out if we needed to do um, multiple regression. So this tabbing down to 8. So I think that's another way to get to the correlation coefficient. So this says that you put the data in, you go to stat and tab to calc. So you go to stat and tab to calc, and then you go all the way down to 8 for this linear regression. Hit enter. And then you tell your data, calculate where your data is. So your X list, I was at 1. My Y was 2, second, and then 2. And then see, here you have to leave the frequency empty. So I know the other one, the other test we have to put a 1, but this one you leave it empty. And you also leave the store regression equation empty, and you go to calculate. And you look for R and C. There's not R squared, but R, correlation coefficient. And that's what you have. That's another way of getting to it, okay? Um, let me see. How's this? This is I thinking here. This. So as far as showing your work, you just put the main command that you use. So you don't have to put every single detail of the command. So one thing is, you could say that you use this, either you use this 8 linear regression, that would be your main command, or that you use the, let me go back to this. This F linear regression t-test. Those would be like the main commands that would, let me know what command you use. So you just put the main command that you use. And I would say the main one would be either you use this F linear regression t-test, or you use this, this number 8 here, linear regression. That would be fine. Okay. Main commands for that. Because those commands will pull that up. Both of those will pull them up. Okay. So we can use either one. And then just put as much notes as you need, because you're allowed to use the review guide. So put as much notes if you need to supplement that on there. And as far as what do you think about this? As far as the correlation, what do you think about the correlation? Because here's the value. So isn't that kind of close to 1, right? Let's see. Yeah, and it looks like on here I didn't put anything like this is like a little generic answer key. I only had that R value. It looks like it didn't answer the other part, which said it wanted to talk about the the strength. But at the bottom we say that if it's strong positive relationships are close to 1. So I would say that's pretty close to 1. If you look at your graph here. See, because here's 0.5, strong positive linear relationship. So you want to say something like that. So, um, strong positive linear relationship because close to a positive one. Because R is close to one, and R is what? It is the correlation coefficient. So because the correlation coefficient, which is R, is pretty close to one, you see on this graph, it's past 0.5. If you have to choose, is it, strong positive, strong negative? Or is that what they were asking? Let's see. Does the result suggest a strong positive linear correlation or a strong negative linear correlation? A perfect positive or a negative linear correlation, or no correlation, or a weak linear correlation? Yes, I would say strong positive relationship, and the reason why is because it's pretty close to +1. Okay, so we're gonna write that down. All right, class. So let's continue on with problem number 7. Based on a data set, blood platelet counts of women have a bell-shaped distribution with a mean of 280. So that's X bar 280, and a standard deviation of 65. And so a standard deviation S, or S of X, of 65. All units are 1,000 cells per milliliter. Using the empirical rule, what is the approximate percentage of women with platelet counts between 215 and 345? So these are like your X, which is the data value. Data values. And they're calling the empirical rule. So I have a handout, so I can find a handout for the empirical. Let's pull that out real quick. Let's see. I think this is handout from our workbook, let's see, about the empirical rule. So I think this would be in section chapter 3. It's definitely in chapter 3. And I think this is section, I think it's section 3.2, I think. It's either, I think it's 3.2 or 3.3. I think it's 3.2. But it has measures of variation, empirical rule, normal. So Chebyshev's theorem applies to any distribution regardless of its shape. However, when a distribution is bell-shaped, or what is called normal or symmetric, the following statements which make up the empirical rule are true. That about 68% of the data values will fall within one standard deviation of the mean. So that means k equals 1. Approximately 95% of data values will fall within 2 standard deviations of the mean. So k equals 2. Or approximately 99.7% of data values will fall within 3 standard deviations of the mean. So with the empirical rule, we're limited to these 3 percentages only. We need to still use this idea, x equals the mean plus or minus the k times the standard deviation, but we don't use this part. This is 1 minus 1 over k squared in parentheses times 100 for a percentage. This is Chebyshev's part. So we don't use that formula for the empirical rule. Okay. So I'm going to write down the formula. Which is x equals mean plus k times s, and also x equals, I guess we put x of 1 and x of 2, mean minus, well, let me put plus on this side and the minus this. And properties apply to data sets having distributions that's approximately bell shape. About 68%, yes, I just read that. Just read that. Okay, look, there's the formula. I didn't see that. Like, there's the formula right there. So I just separated them. So this would be like, because it's a minus, this would be like below the mean. This one with the plus is above the mean. And so this is, I can make this x1 215 on the lower end, and make this x of 2 345. So if I do x of 1, I make that 215 equals the mean x bar, which is 280, minus k, I don't know what k is, but s is 65. So I'm going to solve that for k. Over here, x of 2 would be 345, the other data value. Mean is 280 plus k times s, which is standard deviation, which is 65. So almost the same, except the 215, the 345, it's different. Okay. So I want to solve for k. So here I would subtract 280. Divide both sides by 65 to find out what k is. So let me see on the calculator. I subtracted 280. So what is 215 minus 280? It's a negative 65. And I divide that by -65. That gives me 1. Looks like my K is 1. And I think I should also get that if I think I only have to use one formula, but I think I can check it. I should be able to get 1 as well when I do this side. So this side, I'm going to subtract 280, subtract it. -345 minus 280 is 65 equals 65. Okay. You can divide both sides by 65. And 1 equals to K. And they were asking, what were they asking? Using the empirical rule, what is the approximate percentage of women? So we're associating K to be 1. So when K is 1, it looks like that's about 68% then. With K is 1. So about, because you got K equals 1, that means that about 68% of all data values fall within 1 standard deviation. About 60% of all data values fall within 1 standard deviation of the mean. Okay. So you want to be able to do that on your final, right? Solve for K to determine the percentage that's needed. Now, what I did, I was looking at my detailed solutions here. I I didn't like literally solve for K, but this is another way of doing this. Because you know this formula, and you know that you're limited to K equals 1, K equals 2, K equals 3. So I kind of did it like 3 times. Like I basically, I actually like instead of solving for K, I let K be 2. So here I have my data values, my endpoints. I substituted the mean standard deviation, and then I let K be 2 here. And then I wanted to see my endpoints, what that gave me. So I didn't substitute my endpoints. Here I got 410 and 150, which was off, because remember, we wanted them to be 215 and 345. So when I let K be 2, that was, see, these were off. When I let K equal 3, that would see these were off. But when I let K equal 1, see how I have stars here? When I let K equals 1, and I put into this formula, and then my endpoints ended up being 345 and 215. And so that's how I got around it without doing algebra and solving for K. But I had to do my substitutions, 3 different times, right? And I'm doing the upper and the lower. So basically six substitutions. So that's another thing we can do if you like, or if not, then just solve for K. And if K is one, then it's related. If K is one, then you need to know, like, you need to know K equals one, K equals two, K equals three. And this is for empirical rule. K equals one, you need to know that's associated with the 68% rule. If K equals two, then you need to know that that's associated with the 95% rule. And if K equals three, that's associated with the 99.7. And that's because this is the empirical rule. So you do have to know that. Chebyshev doesn't have restrictions like that. But the empirical rule does, you are limited to Ks. So you just have to know, they sometimes call it the 68, 95, 99.7 rule. That's where they get that from. Okay, let's see. Number 8. The mean SAT math scores for selected states are represented in the frequency distribution below. Find the sample mean using the rounding rule for mean. Okay. So you can do this longhand by hand calculations, and then double check your work using the calculator, if you like. And or you could just use one or the other, either the calculator or the longhand work. And what this is for a group. This is for a group frequency mean. And the formula is summation of F times XM, which stands for frequency times midpoint, divided by summation of F. So you're adding up all the frequencies. So then you'll have to extend this out and you'll have to figure the midpoint. And so with the midpoints, remember you have to add, in this case, the 478 plus the 504, and then divide that by 2. So this score, these are like your class limits. They're counting numbers. So 478 plus 504 divided by 2 is 491. Go ahead and find all the other midpoints for these. Go ahead and add the lower and the upper, and then divide by 2. You want to put parentheses around those. I'll do the same. So I'm taking 505 plus 531, put parentheses around me, dividing it by 2, gives me 518. Maybe 5:45. Yeah, doing 5:72. It is. I'm getting 599. That's my midpoints. And then I would have my frequencies here. So now I'm gonna sum my frequency, add those up, and then I'm gonna multiply the frequency times the midpoint and make a new column for that. So I'll do frequency, which is 4 times 491, which is 1,964. So I'm going to show my work just for the first row, right? Row. 3,108 for the second product. 1,090. 1,144. 1,198. And now I'm going to sum this, sum the product of the frequency times the midpoint. And I'm also going to sum the frequencies. Let me do the frequencies first. Page 60. I'm going to sum these products. So I got 8,504. And so now I have explore. So F times midpoint total 8,504 divided by summation of F, which is 16. $531.5. And sample mean using a rounding rule. So you want to round one more decimal place, right, than how your data normally shows up. So your data shows up as county numbers. So one more place value will be to the 10th place, but it already turned to the 10th. So since these are county numbers, the mean would be rounded to one place value beyond that, but it already has one place value in 10th place, so it should be good. Yeah. Now, for the calculator part, because you can also double check this using the calculator. In the calculator, you want to put the midpoints into column L1, and you want to put the frequencies into column L2, and you want to press the main calculator command is the one variable stats. So you get that by going to stat and on your list and in your frequency list. On the list, you want to identify your midpoint column. And for the frequencies list, you identify where the frequencies are located. I'm gonna try that and see. So I think
You have to input our data, so go to stat, edit, and we want to clear L1, because remember we had data from a previous problem. Clear L2. Go back to L1, L2. So let's see, I have here L1 are the midpoints. Okay, then go back and L2 is the frequencies. Input your frequencies. Okay. Okay, let's see. So now let's try we got that. Let's go to stat, calculate one variable stats. Tell your calculator where you put your data. So X list. That's for the midpoints, which is second one. And then the frequency with let me clear this. I'm not sure I'm not sure that that's the right one. Let's see. So stat, calc, one variable stats, list, and frequency list. You know, put the column. You have frequencies which I have up to calculate. And we're looking for the mean. Yep, here it is. Right here, X bar 531.5. See how that matches here? Yeah, so we just stat, calc, one variable. The stat, calc, one variable stats. This is L1. Frequency versus L2. Okay, so I think that's all. You know, you have a choice on this one. You know, you would have to figure, well, even if you do it on a calculator or you do the formula, everybody still has to calculate the midpoints. And then, because even the calculator, you put, you know, you identify your lists and your frequency list. So the list is where the midpoints are at. So you do have to figure the midpoints, all of them. And then there's a frequency list. So
a few recommendations right on that. You can either do it by hand using this formula, but then you have to complete this F-test exam, or you can go into, you can do it by hand, you use the calculator, and then you have to be familiar with the list and frequency list. Okay, you can see that. And let's see. I was trying to get to 12 and take, second part or do a little break or take a second part of recording. So I was trying there's 25 pounds. I was trying to get to 12. So I'm on 8. Let's see if I can do 4 more. I think we got everything covered on 8. And as far as the commands go, here's the commands at one variable stats. And you could tell me about the list, frequency list. Okay, so let's see. Let's go to 9. Okay, let's see. Find the coefficient of variation for each of the 2 samples. Then compare the variations. Round results known as tenths. Listed below are contributions in dollars made to the 2 presidential candidates of the election. All contributions are the same zip code. True. So let's contributions in dollars made to 2 presidential candidates. 2012, all contributions are from the same zip code as the author, whoever. Okay. So, coefficient of variation. Okay. So let me write this down, the formula. So C bar equals the standard deviation over the sample mean times 100. So S sample mean times 100. Now sometimes the variance is given. So if variance is given, we're going to use C1 equals the square root square over the sample mean And remember standard deviation is S. Let me see if I can show you some sheets in my notes. Getting that from this would be from chapter 3. These are like notes from our notebook PDF. So you can see your formula here, standard deviation over mean times 100%. We use C-bars to compare standard deviations when the units are different, so I should write that down. We use C-bar to compare standard deviations when the units different. And I have some notes here about, see this here? The square root of the variance gives us back the standard deviation. And that's what was going on here, square root of the variance. And I think I had an example where we took the square, see where we're taking the square of the variance, see? They give the mean and then they give the variance, not the standard deviation, the variance. You see that? So we take the square root of the variance. So when you take the final, you just want to, pay attention to whether the standard deviation is given or the variance. If the standard deviation is given, then you want to, insert that into your formula and find that out. But if the standard deviation is not given, but the variance is given, then you want to take the square root of that. Square root of that variance then, okay? Okay, so is that a time to review that? You looking at that? So just have two formulas down, and this is, again, this is just sort of variance is given, the variance is given, we'll use this. If not, we'll use that. Top lump sum deviations given. And these are percentages, so let's put this in here because we do want to have a percentage when we're done with that. And we'll have to put all our data, you can enter this into L1, and then you can enter this into L2 if you want. But what we're trying to do is find a standard deviation and the means for all that data so we can use it the front. And I'm gonna use a little subscript. Okay, and we should be able to find the standard deviation, the mean, by using stat and calculate, right? So we're going stat and okay, let's first enter the data. So I'm gonna enter Obama's data. Oops. If you mistype, you can go back and type it again. Excuse me. It's hope I entered those correctly. I'm gonna put um um McCain's data in and I'm gonna just put it in now into L2. And you want to make sure that you don't have unequal columns, because then you have a domain error issue. See how one column is longer than the other? So they should have the same amount of data on the count. Yeah, it should have 15 data values. The first one does, but the second one I made a mistake. Go back and double check where it left off. Make sure you have the same amount of data. 40 through 250, 700 through 50, 500, 1250, 1500, 500. Oh, so I went to 40, then I need another 500. And that's okay. I can put, it doesn't have to be in the same order, I can input it at the end. That's fine. You want to make sure you don't have unequal amounts of data in the column. That'll give you the amount of issue. Okay, so now let's see. We need to find the standard deviation. So we want to use stat, right? And calc and one variable data. Window the stats. This one, yeah, that's where our data is at. You want to leave the frequency list vacant because this you only put frequency list when you have group data, when you have frequencies or group data. And we don't have group data. So you want to make sure that you list one and you'll leave frequency list leave vacant. And we're looking for the means, need the sample mean and the standard deviation. So the sample mean, and let's see, oh, this says round to the nearest tenth. I don't want to have round off error, so I'm going to record as much as the data as I can. So I'm going to do this. So I'm supposed to have the sample mean at the bottom. So I'm going to write all that down. Because I don't want to have round off error. If I round this to the tens and then I round the final answer to the tens, I could have round off error. I don't want to have round off error. So I'm going to put as much as the data in there. And I need, that's the mean. I need the standard deviation. And that would be this is what you should be getting. If you're not getting this, then you maybe had a typo or you didn't put all the data in, but you should be getting that for the sample mean, and then the standard deviation is S of X. So I should do this. That's I have this here, see, and you can use S or S of X, and that's what that's why you want that one. So 523.209582, and then times 100. So 523.209582 divided by 653.86667. I think there's a way to store it. There's a way to store it, but that's, I mean, not a lot of data values to type in. And then times 100. And then this is what I'll round off to the nearest tenths, like they said. Look at the neighbors. A neighbor of 5 or more, no, it's a 1. So we have 80.0%. That's for the CVAR, which stands for coefficient of variation for a boundary. And then for McCain, we go back to that calculate one variable data, and then you change the list to L2, second L2. So for him, it's list L2.
And remember, you leave the frequency list vacant. And I would say, make a note to yourself, because sometimes people miss this, because sometimes maybe they have done group data and they have something, like a column here, and they forget to, clear it. So sometimes they get that wrong, so just be alert on that. Or they have the wrong column there. Or they shouldn't have a column, or they have a wrong column, and something like that. You don't have something with an error, so be careful. We only use the frequency list when we have group data. So we don't have group data. Okay. So we have two different data values, but that's something that's different. Okay, we're trying to find the sample mean, standard deviation. So for McKean, so this X bar is the sample mean, and that goes in the bottom. So you should be getting this 458.5, and then repeating 1, 2, 3, 4, 5, 6 threes. You should be getting this for McCain's data when you use your stat calc commands. And then the standard deviation is this S of X. So it's 418.422013. So if you're not getting that, then you have typos in there. And then type that in. Oh, then don't forget to here times 100. Okay, so 418.422013 divided by 458.51. I mean 3. And like I said, there is a way to store that 1 times 100. But there's not like a lot of data you have to type. But you should be getting this 91 and 2, 5, 2, 2, 5, 6, 4. And it's a percentage, and you're rounding it to the nearest tenths. Yes, it's 2 is in the tenths place. Then look at the neighbor. Is it 5 or more? Yes. So then we add 1 to the 2 for 91.3%. That's for this coefficient of variation for McCain. And then the question was, to compare them. So which one has more variation? I'd say the larger one, right, which is McCain's, has more variation because it's larger. These are the notes on there. So here, there is more variation in the McCain than the Obama political contribution because it's larger. And yeah, you're specifying which one's larger, which one has more variation. And then again,
Yeah, we can just say that McCain's has more variations. Oh, here we go. There is more variation in the mm, mm, this data. Okay. And then the President Obama data political contributions. Okay. Variation is spread out. Okay. And again, if the variance is given, then you want to take the square root of that. So just remember that, because on your final, that it's possible that they could give you a variance instead of this standard deviations. So like in these past notes here, in this problem, let's look at this problem right here. The magazines. So they give you the variance. And see here they give the variance too. 23 and 62. So you'll notice that C23 is square rootable, and 62, see, square rootable. So just be alert for that, okay? Sometimes you have to do that. Okay? All right, let's see. Okay, I'm getting tired. I was trying to get to 12 because there's 25 problems. I was trying to do the first recording at least to 12 problems, but I think I'm getting tired. I'm at 10. Let's see, can I do two more? Should we try? Sorry, let's see, 10. The tropical cyclone reports, which is published by National Hurricane Center, reveals that maximum wind speeds in miles per hour for tropical cyclones in the Atlantic Basin. Find the 5-number summary and the interquartile range for these data. Okay, so you want to put all the data in, put that in L1, and you want the main command you want to do is one variable stats. So that was what I was going to mention over here. Like you put the formula and the substitutions and then the calculator command. So you got the formula, the substitutions, and the calculator command is basically this stat calc one variable stats, right? And this is also helpful, but you probably want to make notes to yourself for that. But you leave that vacant. But other than that, it's the one variable stats, right? To get to that. Same thing for the tropical cyclone reports. You want to put all the data like in L1, and then you want to use stat calc way various stats. And then we'll scroll down to find the 5-number summary, which involves Q1 and Q2, the quartiles, Q3. Okay. So let's see. I don't know what kind of, what is put your data in? Let me just see if I can anything with the quartile or something. Okay, go ahead and put your data in. Let me just look at it. I do have this, which talks about outliers, but I do see this has the IQR, in case you forgot what that is, the interquartile range. It's the Q3 minus Q1. So you run that. And then I have this, I put it to give you a sample of the 5 number summaries. So let's see. 1, 2, 3, 4, 5. Yeah, here we go. Max. So yeah, like a max and a min on a box plot. Max and a min. And then here's your Q2, median. Here's your Q1 and Q3. Here's your 5 number summary. First quartile. The median, which is the second quartile. The third quartile. Min and max. There's your 5 number summary. And this is shown on a box plot. And remember these whiskers here? Remember these whiskers, if they're the same length, you know, see how you have numbers here? You can find the length, like this is 3200 minus 3100 leaves that with 100. This is 2800 minus 2700, which leaves this length as 100. If those whiskers are the same length, then they're symmetric. This data, even though you don't actually have the actual data, right? You don't see the actual data in this box plot. You know that the distribution of the data is symmetric because the whiskers are about the same. So this is a really nice picture to show you that. See this here? So see how this is symmetric distribution? See how this box plot, see how the whiskers, these are your whiskers, right whisker, left whisker, but they look like the same length. Whereas this is, remember we did left skewed distribution earlier, left skewed. The data tapered off, remember? The left-hand side of the peak. So this is kind of what the box plot would look like. See how this whisker is much longer? See that? See this whisker is much shorter? And then this is right skewed. So see how much longer the whisker is. Okay, so that's a nice picture. And then here's also another nice picture to show you. So again, this whiskers are about symmetric. Left skewed, see, it's longer on the left side, the whiskers longer on the left side. Right skewed, see, the whiskers longer on the right side. And then there's your the values of, like, if you were to figure the 5 number summary, the value of your median is Q2 and Q1. So on the left skewed, your Q1 would be the smallest mean value. Here in symmetric, they're all the same, equal. And the right skewed. So the Q1 is smaller than the Q3. And then here's one more last picture. I like this because see, it says your mode is 10, median is 20, mean is 30. Here, median is 20 because it's median is middle, so middle stays the middle. But look now how the mean is more. Mean is 10, mode is 20. Okay, so negatively skewed. Okay. All right. So yeah, sometimes if you don't actually have the data given, but you're, um, well, let's see. Yeah, if actually I was saying if you don't have the data value, but data given, but if you do have the data given, you would be able to figure out the value of the mode, the median, and the mean. The mode is how many times the data value appears, right? The mean, you're kind of adding them all up and divide by how many you have. The median is the middle number. You put in order from smallest to largest, it's the middle number. So if you know that the mode is smaller than the mean, that would tell you that your distribution is positively skewed if this is happening. See, the mean is much smaller than the mode, but the median would still have to be, have that number for that. Okay, so for us, did you put your data in? Well, I mean, it's important to mention, I went off a little bit, but I needed to put that in somewhere. That was a good place to put it in. I had asked you to put your data in. Did you put your data in already? Let me go back to L1, clear that, put that in. Okay, so I believe I put all the data in. So I'm gonna go stat, calculate one variable stats, and my data is in L1. So change that to second, and then the one sign for that. That's your list. And basically, you leave the frequency vacant. And this is your main calculated command. And you're going to tap down 2 times, right? So it looks like you have to tap down about 5 times, right? You want to tap down. I think it was about 5 times. Just to see. So remember, you have a minimum. And remember how that page identified it? Remember how this identified it? Maximum, minimum, median, and first quartile, third quartile. So that's kind of where I'm getting that from. But if I start in the box spot, like with the minimum, which is the mid, then, and also on your picture too, this is helpful. Minimum, Q1, median, which is Q2, Q3, and then max. So that's also helpful. The minimum, and then Q1, which they're calling it as first quartile. So that would be 50, right? And then the median is the Q2, which your calculator calls MED. And Q3, 100. And then maximum 150. The minimum is 40. Q wood is 50. Median is 80. Q3 is 100. Oops, fix that. Let me see. And then maximum is 150. And then the interquartile range, which is called um, IQR, which is third quartile minus first quartile. Minus 50. 50. And what I was going to say, I had something to talk about the interquartile range. This is important. Let me go back to that page. So if box plots for two or more data sets are graphed on the same axis, then distributions can be compared. So to compare the averages or the centers, use the locations of the medians, which we call Q2. To compare variability, the spread of the data, use the IQR because you're doing Q3 minus Q1. Larger IQRs produce more variability when comparing box plots. Data sets with a greater spread variability have a larger IQR. That's important to note. So maybe I can put that little note here. Let's maybe look at the comment you have somewhere, but larger IQRs produce more variability. Which is what is more variability is a greater spread. Okay, did we do two more? Let's see. Let's go 11. The monthly utility bills in a city have a mean of $70, a standard deviation 8. So 5. the Z-score so X minus X Y O. So let me see. Did I print anything? Let me just check up. I don't know extra things to say about this. I'm not sure. That would be then chapter. This is chapter 3. Well, I do have something here about Z. So remember this -2 to 2 range? Most of the normal distributions contain between the boundaries of -2 to 2. If a Z-score exists within this range, when you're plotting your Z-scores, if they're within the -2 to 2 range, then that means our data value is considered ordinary and usual. If our data value is unusual, it'll be outside of these brackets. So it looks like on this example, we had figured that the data value calculus test score was 65. It's considered usual, ordinary because it is corresponding as a score. It's true. So here, within the range, this score, calculus test score is 65. It's considered usual, and because it's corresponding to this score, which is 1.5, is within that range. Okay. I'm trying to see there's any other handouts. These ones. I don't think I printed to this. Let me just check one more section. There is a page when we start Z-scores. I think it's 3.3. That have information about it. But I don't think I printed it. But if you look at your 3.3 notes, it'd be good for you to look at it. It's not necessary or anything. But you can figure, in this case, when we figured the Z-score was 1.5, see 1.5 sits here between -2 and 2, so it's ordinary. So because the Z-score is ordinary, that means its data value was ordinary. If the Z-scores are here, that means the data value is probably not usual, right? So here, you just need to substitute. You need to know your formula and then substitute Oh, it's 71. So that means the 71, like that's the X, the data value. Divided by 8 is standard deviation. So 71 minus 70 is just 1, 8. Okay, this very small value. So $71 is 0.125 standard deviations, and it's above because it's positive. Above means this z-square is positive, not negative. If it's negative, then it'd be below the z-square. Mhm. And I guess I could, at least I have my book here. You might open up 3.1. Pretty sure that's where we got that from. Now here's what we're talking. We're talking about the mean mode. See, it's positive skewed, negatively skewed, symmetric. If the mean, median, and mode are all the same value, all or about the same, like all about 5, all about 10, symmetric. But it's negatively skewed. Oops. Yeah, I'm trying to look for z-score. Right? Let me see. I think it's in +3. P3. The z-score represents the number of standard deviations the data value falls either above or below the mean. Okay. Alright. Okay, one last one. I know, then I'll stop recording in the second part later. An issue of brokerage report discussed the capital spending of telecommunication companies in US and Canada. The capital spending of thousands of dollars for each of 27, let's see, 1, 2, 3, 4, 5, 10, 15, 20, 1, 2, 3, 4, 5, 6, 7, 28. Looks like I have 28 values. It looks like I have 28. I'll say 27. Right? It looks like there's 28. Identify potential outliers. Okay, outliers. Okay. So remember we saw that paper earlier with the outliers. Can we do that? Well, we have 2 formulas for the outliers. So this is in my workbook talking about here's an example here with outliers. See these formulas here? So data value is less than Q1 minus 1.5 times IQR. Data value greater than Q3 plus 1.5 times IQR. So when you plug in your Q1 and you figure your IQR and you have a data value you compare it to, then you want to find out, do you have is there any data value that's less than this? Is there any data value that's greater than this? Because if so, if the answer is yes, see, you have any data values that are greater than 36.5 is yes, you have to look for it, that means you have an outlier. If the answer is no, the answer is no, then if the answer is no on one of these columns, you still gotta check the other one and make sure yes or no. You gotta check both of them, okay? All right, so let's try that. So you're gonna put the data value into your column, and then you want to, your main calculated command is that California, that, because once you get that, that'll get you maybe Q1 or Q3 that you're lacking. So go ahead and start putting in the data. And I'm going to write down the formulas. Let's see. Okay, so those are, I'm going to write the form like this. And let's put the data in. Stop. Clear Illinois. I'll put all that data in. But if you put your data in, you can go either up and down vertically, or you go horizontally, but just, try your best, not to stick out. Just, okay, I put all the data in. Let's see. I put in the first statement. You always want to double check and all that. But you have the right data. But I'm going to stat, calc, and then one variable stats. And all my data I looked in O1. Leave my frequency list vacant. That's if you have group data and if you have frequencies, like usually you put midpoints and stuff like that. I'm not doing that. So. We need the Q1 and the, do you remember what the IQR is? Remember we needed that? Remember the IQR is Q3 minus Q1. Okay. Okay, so we have Q1, and if you scroll down, I have 652.5. See that right? Nope. Let's see. I have an error somewhere. Q1. I think you're supposed to get 660, I think. I think you're supposed to get 600. It seems like I have an error. Let me go back to that. It's because I'm getting sleepy as a type. Sorry. Let's see. Mm, mm. Okay, let's see. So 9, 6 of this. Okay. I'm just checking the data. Oh, here's the error towards the end. I only typed in 180. I was supposed to type in 1,800. Okay, so now that was the error. So one little mistake throws everything off. A stat, calculate one variable stats. and everything's in my first column. And I'm looking for Q1, so tab down. And I'm getting 660. Yeah, that's what it's supposed to be. 660. Okay. Minus 1.5 times IQR. And IQR is Q3, which Q3, let's keep scrolling down, is 4749.5 minus Q1, which was 660. So 4749.5 minus 660 is 4089.5. And then times 1.5. 6. Okay, so 660 minus 6134.25 is negative 5474.25. So your question is, are there any data values that are you see this here? See this inequality? This is the less than. See data values, question mark. Are there any data values that are less than a negative 5,424.25? And you would say no, right? Because you don't have any negatives at all. They're all positive. So nothing's less than that negative. So no. So, but that doesn't mean you stop there. You still have to check the other formula. You gotta check this one. So this formula goes this way. Here's your formula, and you want to find out if there are any data values. Just points to this. Yes. Are there any data values? So you ask, this one says, this one asks, are there any data values that are greater than, and better figure out what this greater than this guy. So let's see Q3. So for Q3, what was Q3? Go back to stat, calculate one variable stats, and go back to Q3, scroll down. So I have Q3 is 4,749.5 plus 1.5 times IQR, and you already know IQR is 4089.5. 4749.5 plus, so you're gonna do 1.5 times that value. 1.5 times 4089.5, which is 6134.25. So then I add 47495. I think let's look again, let's see. So Q3 is 4749.5 plus 1.5 times. Well, you know what I could have done is, see, I already found the IQR over here. See, IQR times 1.5, right? 1.5 times IQR. And that's already, we already figured that. See, it's right here. 1.5 times 4089 is 6134. Oh, I have it. So that's right. 6134.25. Okay, so that was correct. So then did I add? I don't remember if I added 6134.25 plus 47495. Yep. So that, I'm wondering if I made a mistake. I thought I had something different over here. Oh, look at me. It looks like that's what I'm getting. 53,629.25. So the question is, are there any data values that are bigger than that, bigger than 53,000? I don't see any that are bigger than 53,000. So I just want to double check because on this paper here, when I did this calculation, I said here that there were 2 outliers. See this right here? Because I got the same thing on the left side for this formula. But when I did the second formula, see, I got 4749. Oh, I'm off with it. There's a decimal missing. Oh, Q3. Okay, let me go back. Is that why I'm off by a decimal? Stat, count, variable stats. Q3. Yep. See, one little mistake throws it all off. See, there's a decimal error. See? So you see, on my Q3, I had it here, but look, it's real small. See that? And see Q3, is it? See, Q3 is 4749.5. See how it's real small right there? So one little mistake throws it off. Okay, so now let's see. 4749.5 plus 6134.25. That's more like it. 10,000, comma, 883.75. Okay, so the question is, are there any data values that are greater than this side, than this? Are there any data values that are greater than 10,883.75? So you would say yes, because see, there's one right there, 11,000, that's bigger than 10,000 something. Oh yeah, and then look at this one, 17,000. See that? Yep. So it looks like we have two outliers. Yeah. So we have two outliers. So they are the 17,341 and the 11,189. And that's because which are larger than this 10,883.75. Okay, which is coming from the second formula. So the first formula that we used, we didn't have any data values that were smaller than the negative number here. But on the second formula, we did have some data values that were bigger than this 10,883.75 value. Okay, so that's 12 problems. So I'm going to stop there and then take a break, right? And then do the second recording at a later time. But because there's 25 problems. But I also covered a few extra things, right? Just to make it more wholesome or general definitions that we use. So that's why it took a little bit longer. Okay, all right. Well, stop. Take care.